All right, let's start rocking and rolling. No beating around the bush today. Let's see. Okay, chapter 7. Hi, Brianna. How you doing? Let's see. Yup. Here, I'm gonna make a master list here of all the chapter 7 stuff. I know this is gonna get lost. I can totally do some percent units problems. In fact, what I think I'll do. Let's see. So we've got chapter 7, chapter 8. Totally. Dude, never apologize for asking questions. That's literally how learning happens. Oh wait, yep. We will have time and room for all. I'm just writing down all the chapter problems. Let's see, Prathana, you had seven. Okay, so let's see, and then homework 7, 17, 18. All right. Okay, cool. So here's what we're going to do. So we've got two long lists. We've got some requests for okay, okay. So so here's what I'm going to do. I'm going to write an example problem on the board of what to of an example of some practice stuff with the percent concentration situation. Jen, it sounds like you need a jump start on a couple homework questions. And then I'm going to start knocking off problems from Carenza's list and Prarthana's list. We can also go over that one. Yep, totally. Okay, let's see. So here, let's go ahead and start with an example from with percent concentrations and such. A solution has a density of 1.128 grams per milliliter. 14.0 grams of solute are dissolved in 78.5 grams of solvent. Determine the percent mass and the percent mass to volume. All right, so that's, Brianna, there's an example of concentration percent units. We'll come back to that. We'll come back to that. All right. So, Susan, looking to jumpstart your effort on homework 7, numbers 17 and 18. So both of these are dilution equations. So it's M1V1 equals M2V2. So I don't know if that's enough information to kind of jumpstart you. If not, I can totally come back and shine a little more light. But for now, I'm going to roll and start knocking out a few of these practice problems from the chapter. Starting with chapter 7, number 27, which I still have to find. All right, here we go. So a sample of N2 occupies a volume. Oh! Hey Winnie, how's it going? It's good to see you. All of a sudden I was like, I haven't seen that handle since, well, it's been like 2 months. I hope your summer's been less strenuous than ours has. Okay. Before I jump into this problem, Susan, I'm gonna give you the next hint. Oops, nope. So this is a hint for what was that? 17. It says that oh, dude, I bet I didn't know you were taking summer. Yeah, if you're taking summer session, it is it never stops. So you have 0.3 molar. And you have 50.0 milliliters, right? In this problem. And then it says 2 then you're told that 75.0 mils are added. So here's the thing. There's V1, right? This is M1. V2 V2 will equal V1 plus the added amount. Susan, so that that should give you a jump start on solving that problem. Winnie, it was so good to digitally see you. Totally pop back in. It's always fun when students from previous semesters just pop in and say hi. It's always a blast for me. Any free response questions on Lab Quiz 10? Yes. Think there's one or two. Okay. All right. Now, at long last, let's dive in. So number 27. So we have a sample of N2 gas that occupies a volume of 375 milliliters at 25 degrees Celsius. Whenever I see a temperature in degrees Celsius in a gas law context, I automatically convert to Kelvin because you're just going to need to at the end of the day. Okay, and we're given also a pressure of 2.0 atmospheres. And then it says determine the temperature in Celsius at which volume the gas would be. Okay, so this is important. This is V1, T1, and P1. We're given our V2 is equal to 525 milliliters. we are told that our P2 is the same as P1, and then we're asked to find T2 in degrees Celsius. Now, it's important to note that you still need to convert to Kelvin, all right? If you're going to use the combined gas law, the temperature must be in Kelvin. Since they asked for a temperature in degrees Celsius, we will have to convert it back, but in order to use the combined gas law, we have to use all temperatures must be in Kelvin. All right, so we weren't mentioned, moles weren't mentioned, so those will drop out. Pressure doesn't change, so it drops out. So our equation here simplifies to V1 over T1 is equal to V2 over T2. We need to isolate T2 on one side of this equation. We can do so. Well, first we got to get it out of the denominator. So let's multiply both sides by T2. So we get T2 times V1 over T1 equals V2. And then we got to isolate T2 on one side of the equation, so we multiply both sides by T1 over V1. So now our expression simplifies to T2 is equal to V2 times T1 over V1. Now we punch in our numbers. We've got 370. Oh no, that's V2 up in the numerator. 525 mils times our initial temperature, 298 Kelvin, over V1, 375. Our volume units cancel. So now we go 525 times 298 divided by 375 gives us a temperature of 417 Kelvin. To convert this to Celsius, we have to subtract 273. So that will be 144 degrees Celsius is our final temperature. All right, so chapter 20, not chapter 20, chapter 7, number 27 is a combined gas law problem. All right, we're going to, I'm just going to be bouncing around, so let's hop over to chapter 8. And again, anybody can throw a question in at any time. I'm just going to be we've got a long list of chapter 7 and chapter 8 problems, so I'm going to be hitting those up. And I'll do a bunch of those and then answer some more questions up in the feed and then do a bunch more, etc. All right, so let's see. So let's hit chapter. Chapter 8, number 57, part C. Prathana, this is one of your questions. So, oh wait, it's chapter 9. It would be in chapter 8. Calculate the grams of sodium hydroxide needed to prepare each of the following solutions. So we're being asked to find grams NaOH, 4, and in part C we're told that we have 0.10000 liters of a 0.50 molar solution. All right, so here's the thing. We know that molarity are equal to moles over liters. We're given molarity, we're given liters, we're being asked to find grams, which is all right because if we know our moles, we can convert from moles of sodium hydroxide to grams of sodium hydroxide using the molecular weight. So step number 1 is do a little algebra. We've got molarity is equal to moles over liters. So we can isolate moles on one side of this equation if we multiply both sides by liters. So moles of sodium hydroxide are equal to its volume in liters, 0.100 times 0.50 moles of NaOH over liters. Volume cancels, and so we have 0.05, I think. Yeah. 0.05, let's see, 2 sig figs, 0 moles of NaOH. All right, so now we have to convert from moles of NaOH to grams. And to do this, we need to know what the molecular mass is. Sodium, 22.99. Oxygen is 16.00, and hydrogen is 1.01. So this is all going to add. Oh, wow. To 40. 40 on the nose. So this is 40.00 grams in 1 mole. Moles of NaOH cancel. Now we crunch our numbers. So my calculator is giving me the answer is 2, but we know we need the right number of sig figs. So this will be 2.0 grams of sodium hydroxide are needed to make 0.100 liters of a 0.50 molar solution. All right, Jen, quick question. Or not Jen, sorry, Susan. Oops. Really? Let me recheck the numbers they give us. Excuse me. Okay, Kate, you think 57C is misleading? Oh, wait, no. You said B is misleading sig figs wise. Yeah. Oh, thank you. Okay. All right, Parthana, I'm looking for Lab 10 question 4. Okay, here it is. Why is it that the Erlenmeyer flask need not be dry? Why is it not necessarily necessary? All right, so this is a question coming in from Lab 10. Question 4. Lab 10 question 4 says, why is it that the Erlenmeyer flask need not be dry, and why is it not necessarily to precisely measure the 25 mils of water added to the flask? All right, so remember here we're doing a titration. All right, we're doing a titration, and the Erlenmeyer flask is the thing that holds the analyte. All right, and the reason why, so if this has, let's say it has droplets of H2O in there before, so this is, let's say you got some droplets of H2O, you are going to add exactly 10.0 mils of analyte in, right? And then you add approximately 25-ish mils of water. And they're asking, why does it not matter if there's water droplets in there already, why does it not matter that it's only approximately 25 mils of H2O? Why can we fudge this? And to answer this question, I'd like to pose a question to you. So here's my big question. Does adding pure water change the moles of analyte in the flask? All right, think about it. Does adding pure water change the moles of analyte in your flask? And the answer is no. It doesn't. You can add as much water as you want. You're still going to have the same number of moles of analyte, and your moles of analyte determine how much titrant has to be added. So it doesn't matter how much water you put in there, the moles of analyte remain the same. So, does it matter? Does adding pure water change the moles of analyte? No. So you do not need to be precise. With your water measurements. Yeah, Prathana, you got it. You totally got it. By the way, Susan, let me know when you get to if you've gotten to your final volume for problem 17. If you can't get there, holler at me. Let me know, and I'll help push you forward. But once you find V2, that's your next step for getting forward. Of course, you are welcome. All right, let's do another chapter 8 problem. Let's knock one of these suckers off of our list. Let's do chapter 8, number 20. All right. Okay. Okay, Susan, here's the twist. Here's the thing to look for. For 18. We're told that 75.0 mils of 0.20 molar solution has been concentrated to 60 milliliters. Concentrated means that some of the solvent has been evaporated. So this one has actually undergone a reduction in volume. So our initial molarity is here. Our initial volume was 75 milliliters. our final volume is that 60, and it's up to you to calculate your final concentration. So that is how you unlock 18. Alright, now let's do chapter 8, number 20. Methanol is a polar solvent. Heptane is nonpolar. In which of the two solvents are each of the following solutes more likely to be soluble? Okay, so we have two things. We have methanol, which is polar. And then we have, what was the other guy? Heptane. Which is nonpolar. And then we're asked, which is more soluble in and this is where we're given A, B, C, and D. All right, and A is sorry, actually, phrasing of this is slightly off. The question is each solute more likely to be soluble in heptane or methanol? All right, and then they give us the list of solutes. We've got K. Oops, not Ki. KCl. I apologize. My brother keeps calling me. I'm just gonna text him back that I'm in class. Let's see, KCl, which is ionic, rubbing alcohol, which is polar, gasoline, which is nonpolar, and sodium nitrate, which is ionic. All right, now okay. Sorry, I thought it was like an immersion. My brother had a possible COVID exposure situation at his work. And he just texted me that it came back negative, but then my mind was like, negative is bad. I'm like, oh no. And then I'm like, wait, no, that's what you want. You want your coworker testing negative. Okay, so let's answer this. And I'm going to box this in salmon for methanol, blue for heptane. So the thing is, like dissolves like, right? So right out of the gate, we know that something that's polar will be soluble in methanol. Something that's non-polar will be more soluble in heptane. All right? But now with the ionic things, well, that's ionic isn't polar or non-polar. It's not, but remember what ionic means. It means that you have positive and negative charges. And would those positive and negative charges be more likely to dissolve in something with partial positives and negatives or something with no charges? And the answer is it'd be more likely to dissolve in something with partial positives and negatives. So your ionic things will always be more likely to dissolve in a polar solvent than a non-polar solvent. Basically, the only other thing that will prefer a non-polar solvent is other non-polar stuff. Everything else, the polar solvent will dominate. All right, so that is that's number 20. Let's grab another one out of here. How about is 84. 84 is a different kind of guy. Let's take a look. Chapter 8, number 84. Asks a conceptual question. How does the freezing point of water the freezing point of seawater compare to the freezing point of freshwater? All right, now, with these types of problems, these colligative property type problems, there's two things you want to remember. Adding a solute changes the physical properties of the solution. They will be different than the physical properties of the pure solvent. So, seawater is salt water, right? It's got solutes. All right, freshwater more or less is pure. So they're basically asking a lot of solutes versus almost no solutes. There's two things you want to keep in mind: the way solutes affect the physical properties of the solution. You want to remember freezing point depression and you want to remember boiling point elevation. The introduction of solutes will drop the freezing point and raise the boiling point. So for this problem, how does seawater, the freezing point of seawater compare to freshwater? Seawater has a lower freezing point because it has more solutes. Or I should say, not more, has a higher concentration of solutes. Ah, Susan, great question. Okay. Let's see, so that's 84. Let's go ahead and do 99. Ah! Oops. Okay. So let's do one more chapter 8 problem, and then I'll do the homebrewed problem. No, Susan, removed and subtracted are the same thing. Totally the same thing. Oops. So let's look at chapter 8, number 99. Let's see, so you don't subtract when it says, when the wording reads, the solution was concentrated from 75 mils to 60 mils. The concentrated to language tells you that 60 mils is the final volume. You do subtract when it reads, let's see, 75 mils were concentrated, removing 15 mils. When it says remove, that means you subtract. All right, so number 99, we're finding the osmolarity. And remember, osmolarity equals the molarity of a solution times I, where I is the number of particles a solute forms in solution. Okay, so let's look at these. We have A, so whoa, does not mean to erase that much. So we have 2.0 molar KNO3. So the thing is, here, for potassium nitrate, you have potassium and nitrate. So I equals 2, which means that your osmolarity will equal 2.0 times 2. So our osmolarity will be 4.0 osmol. Oh, we've done A. Let's look at B. Okay, so B, we're given a solution that is 1.0 molar of K2SO4. Now, this has 2 potassium cations plus 1 sulfate. So I, here, because it splits into 3 particles, I is equal to 3. So our osmolarity is 1.0 molar times number of particles it splits into 3. So that equals 3.0 is our osmolarity for solution B. C Oh, interesting. Okay, so we've got 2.0 molar of KNO3 and 2.0 molar of what was the other one? Na2SO4. All right, so here's the thing. Osmolarity is the number of particles of solute forms. We're talking about all particles. So our osmolarity will equal 2.0 times the I for KNO3 plus 2.0 times the I for Na2SO4. Questions like C and D. So here, our osmolarity, or sorry, our I for potassium nitrate is 2, but for sodium sulfate, it's 3. So our osmolarity will be 2.0 times 2 plus 2.0 times 3. So that'll be, whoops. So our osmolarity will be 4.0 plus 6.0. So this solution would have an osmolarity of 10.0. Alright, so that was Chapter 8, number 99. Let's take a look at the homebrewed example problem from earlier. From an... Oh no, it hasn't been an hour. No, yes it has. From an hour ago. Alright, a solution has a density of 1.128 grams per milliliter. 14 grams of solute are dissolved in 78.5 grams of solvent. Determine the percent mass and the percent mass to volume. Alright, so first I'm going to start with the percent by mass. This equals the grams of solute over the grams of solvent. All right, times 100%. But the thing to remember is that we're given the grams of solute, but we're not given the grams of solvent. The grams of solvent, I'm sorry, that's my bad. It doesn't equal the grams of solvent in the denominator. It equals the grams of solution. The grams of solution equal the grams of solute plus the grams of solvent. And even though we aren't given the grams of solution, we know the grams of solute and the grams of solvent, so we can solve for that. So our grams of solution equal our solute mass, which is 14.0 grams, plus our solvent mass, which is 78.5 grams. All right, these will add to 82.5 grams of solution. Oh, sorry, 92.5. My bad. All right, now I'm doing math in my head. I'm just going to double check myself. Yeah, 92.5. Okay, that's our mass of solution. So now we have our percent mass is equal to mass of solute, 14.0, divided by mass of solution, 92.5, times 100%. So I've got 14.0 divided by 92.5 times 100. So this comes out to be 15.1%, and that is the percent mass. All right, now that's step number one. Now we have to calculate the the percent mass to volume. Now percent mass to volume is grams of solute over milliliters of solution times 100. And if you look at it, our percent mass, which we just calculated and I promptly forgot, 15.1 grams of solute over 100 grams of solution. What we need is some sort of conversion factor that will cancel the mass of the solution and leave us with milliliters of solution. Right? If only such a thing were possible. The cool thing is it is. This is what our density is. Our density, which we're given earlier, is 1.128 grams per milliliter. So that's 1.128 grams over 1 milliliter. All right. Now, you'll notice we still have to multiply by 100 because that's what this business is all about. So now we just go to town. All right, and we can keep 3 of our sig figs. So this will be 17.0% mass to volume. Let's see. Yep. Okay, you are spot on correct. Okay. Brianna, tell me what part is confusing you? Oh, okay, right. Okay. Yes. Totally. But you'll notice, okay, so Brianna, correct me if I'm wrong, you're probably wondering, where did that 15.1 grams come from? Right? And the thing is, because you're like, initially we had 14.0 grams of solute. Oops. But that 15 is part of the ratio. So you had 14.0 grams of solute in 92.5 grams of solution. Or, same ratio. Whoa. Or you could say that you have 15.1 grams of solute in 100 grams of solution. And we get this one from the percent mass. So the reason why we had that 15.1 grams is we started with the percent mass that we calculated in the first part of the problem. And we got that ratio from the 14 grams of solute in 92.5 grams of solution. Okay, so honest question, and I need a true answer. Honestly, let me know if I made it more confusing. Because if so, there are other ways to explain it. We can get you there. But I just need to know like how you're doing, where you're at right now. So let me know if that helped or if that muddied the waters. Okay. Yep. I totally... Okay, yeah, okay. Okay, so, Brianna, let's work this percent mass to volume thing a different way. So one way to look at it, another way to look at it is percent mass to volume is equal to grams of solute divided by milliliters, totally, of solution times 100, right? Now, we're given that we have 14.0 grams of solute, and in the previous part of the problem, we realized that we have 92.5 grams of solution. All right. Now the problem is we have grams of solution and we need milliliters. This is where our density comes in. The density of our solution is 1.128 grams per milliliter. So we can use it to cancel our grams of solution and convert to milliliters of solution. Because the density tells us that there's 1.128 grams in every 1 milliliter. So we have 92.8 divided by 1.128. That gives us, let's see, 3 sig figs, 82.3 milliliters of solution. Now that we know our denominator, we can calculate our percent mass to volume. Because it'll equal 14.0 grams of solute over 82.3 milliliters times 100, so 14.0 divided by 82.3 times 100, and we can keep 3 sig figs. So this comes out to be 17.0%. So that's another way, and you'll notice actually if you go back in the video and look at how I calculated it previously, the answers are the same. There's more than one way to work this particular problem, which is kind of cool. Okay, so let's do another. Let's bounce to chapter 7. We've done chapter 8 the past couple problems. Let's hit a chapter 7. Okay. Let's see, we did 27. Let's jump to 35. Parts C and D. Awesome! Awesome. Brianna, I'm so glad. Alright, so let's see. Chapter 7, number 35. Anytime. Absolutely anytime. Okay, so here we're told that a sample of carbon dioxide gas, so we've got CO2 gas, we're told it has a volume of 15.2 liters and a pressure of 1.35 atmospheres. We're also given a temperature of 33 degrees Celsius. Again, whenever you're playing with gas law stuff, just convert to Kelvin right out of the gate. This will be 306 Kelvin. There we go. Okay. And then part C, temperature in degrees Celsius. Determine the following for this gas sample. So in part C, they want us to find temperature in degrees Celsius. And they tell us that pressure, they want us to find the temperature in degrees Celsius when the pressure is 7 atmospheres. And the volume is 0.973 liters. All right, so up here we have V1, P1, and T1. Down here we have P2 and V2, and they ask us to find T2. All right, so again, this is combined gas law. P1, so over just a little bit. P1 V1 over N1 T1 equals P2 V2 over N2 T2. Now they haven't mentioned moles, so moles cancel. All right, and we want to find our final temperature, so we need to get it out of our denominator. Multiply both sides by T2. So we get T2 times P1 V1 over T1 is equal to just P2 V2. We still need to isolate T2 on one side of the equation. So we multiply by T1 over P1 times V1, so everything cancels over here. Multiply this side by T1 over P1 V1. So our final temperature is equal to P2 V2 times T1 over P1 V1. We can plug all these in. Our final pressure is 7.00 atmospheres. Our final volume is 0.973 liters. Final temperature, our initial temperature is 306 Kelvin. Our initial pressure is 1.35 atmospheres, and our initial volume is 15.2 liters. One of the things you'll notice, liters cancel, atmospheres cancel. We're left with Kelvin units, which is good because we're solving for a temperature. All right, so let's see. So we've got 7 times 0.973 times 306 divided by 1.35 divided by 15.2. All right, so our temperature, keeping 3 sig figs, comes out to 102 Kelvin, but you'll notice that they want an answer that's in degrees Celsius. So to convert from Kelvin to Celsius, you subtract 273. And so our temperature in degrees Celsius will be negative 171 degrees C. And that is our final answer for final temperature. Okay, oh yeah, let's see. Yes, Esther and Susan, I could totally do both of those. Let me do, sorry, this was 35, part C. For this one, there's also a part D, so let me do part D. And then what I'll do is I will write up an example of stoichiometry and some gas law stuff so that you can work on it, and then we'll circle back to that. All right, so let me just hit up part D, and then I'll totally generate the problems that you guys are asking for. All right, so part D for this problem, they want us to find our volume in milliliters, and they give us a temperature, well, they give us a temperature and a pressure. I'm going to start with the pressure. Awesome. Okay. Let's see, our final pressure is 6.70 atmospheres, and our final temperature is 97 degrees Celsius. But again, anytime you're using the gas laws, you gotta convert to Kelvin. Oh, and this is gonna be a pain. Not that big of a pain, but a little bit of a pain. So these two add to 370. The problem is the last significant digit in both of these numbers is in the ones place. We need a significant digit there, and that 0 isn't significant. So we got to write this as 3.70 times 10 to the second Kelvin. That way it has the right number of sig figs. Okay. We're doing combined gas law. So let's write that out. Moles weren't mentioned, so they cancel for this problem. And now we need to find our final volume. So we need to multiply both sides by T2 over P2. So we get our final volume is equal to P1V1T2 over T1P2. We can plug in our numbers, 1.35 atmospheres times our volume, our initial volume, 15.2 liters, times our final temperature, 3.70 times 10 squared Kelvin, over initial temperature, 306 Kelvin, times P2, which is 6.70 atmospheres. And ATM cancels, Kelvin cancels. We're left with liters, which is a volume unit. Now, 1.35 times 15.2 times 370 divided by 306 divided by 6.7. Now we can keep 3 sig figs here. So our answer will be 3.70 liters. Now, problem. We found our final volume in liters, but they want it in milliliters. So we need to do a unit conversion to get to our final answer. 1 milliliter is 10 to the third liters. So now, when you do this, it says, my calculator is telling me my answer is 3,700 milliliters, but I need 3 sig figs. So we're actually going to have to go back to scientific notation. 3.70 times 10 to the third milliliters. Because 3,700 only has 2, but you need 3 because your answer has 3. So that is the answer for part D. All right, let's take a look. Okay, so I got to generate a few of these here. Stoichiometric and or gas law problem. Esther, you want a Dalton's law type problem. I'm going to do this. Where's my mouse? There it is. I'm going to look at exam 3. Totally. Okay. Let's see, exam 3. All right, how about I do a combo? How about I make this a stoichiometry Dalton's law problem? That sounds exciting. Let's find a chemical equation. Okay. Oh, but that's not a Dalton's problem. All right, there we go. Okay. So, hang on. I'm trying to find the right chemical reaction. Or a good chemical reaction. Okay, well this one isn't a it's not a Dalton's law one, but it is stoichiometry and gas laws, so I guess there's that, and I'll homebrew up the Dalton's law problem in a minute. But let's take a look at this. So, when heated, to 406 degrees Celsius, solid magnesium oxide decomposes into magnesium metal, which is a solid, and oxygen gas. All right. This reaction takes place in a 32.0 liter reaction chamber. If 22.0 grams of magnesium oxide decomposes completely, what pressure will the produced gas have? All right. So that is a stoichiometry and gas law problem. So give that a whirl. Oh yeah. Kate, I can totally do practice homework number 8, or practice homework chapter 8, number 76. Let's take a look. Chapter 876, a solution of hydrogen peroxide in water with a volume of 50 milliliters is diluted by adding 70. Calculate the solution's new concentration given the following original concentrations. Okay, so we have what this problem tells us is V1 is V1 is 70. And then 50 milliliters are added, so V2 is 70 plus 50. And we're also told to use a density of 1.00 grams per mil. number 76. Right. And so for all of these, we're asked to determine the final concentration. All right, and then so for A, we're told that our initial concentration, M1, is 2.0% mass to volume. All right, and actually, I'd just like to point out one of the cool things about this problem is the algebra is going to be the same every time. Right? We have M1 V1 equals M2 V2, and they want us to find M2 every time. So we can just knock our algebra out at the beginning, because we're going to be using this every time. M2 is equal to M1 V1 over V2. All right, so we know our M1, it's 2.0% mass to volume. It's important to keep those units in there, times our V1, which was 70. Just let me make sure I didn't transcribe that wrong. Oh, I did mess this up. It's a 76. Oh, I flipped 76 and 75. I'm sorry. Yeah. Sorry, I messed something up down here. V1 is 50. It doesn't change what our final volume is, but it will affect our answer. Okay, 75 is cool too. Oh, yeah. But the numbers will all be different. They're the same, exact same type of problem. All right, so by the looks of things, milliliters cancel milliliters, and our answer is going to be limited to two sig figs. So here we'll have 2 times 70 divided by 120 gives us a final concentration of 1.2% mass to volume. Is part A. Part B, oh, you know what's so funny? Is these will all come out the same. Right, because check this out. So, watch what happens here. So let's just take part B. They give us our M1 is 2.0% volume to volume. And so here we have, again, M2 is equal to M1 times V1 over V2. 2.0% volume to volume times 50 mils over 120 mils, the math comes out exactly the same. And we're only keeping, so mils cancel mils, keeping 2 units, 1.16% volume to volume. Yeah, we can totally do 73 next. So still chapter 8, number 73. So we just did um, 76. Let's do 73. What is the molarity of a solution prepared by concentrating by evaporation of solvent? 20 to 12 mils, 0.4 molar, K2SO4, solution to a volume of 853. Okay. Well, there's still 76. Still had. So Kate, sorry, I see your thing. 76 was 50 milliliters is diluted by adding 70. So we still have to add 70 to get that 120. Okay, this was 73. So for this problem, we have 2,212 milliliters of 0.400 molar is concentrated to a volume of 853 milliliters. And they want to know what is the molarity, right? M2 V2 equals M1 V1. M1 is our 0.4 molar. V1 is our 2,212. And then V2 is our 853. So to solve here, we divide both sides by V2. So we get M2 is equal to M1 V1 over V2. And our M1 is 0.4000 molar. Our V1 is 2,012 milliliters. And our V2 is 853 milliliters. So milliliters cancel. Yep. All right, and All right, so let's calculate our final concentration. 0.4 times 2212 divided by 853. All right, and we've got to round to 3 significant figures. So that'd be 1.04 molar would be the volume after concentrating it. All right, here, it looks like now might be a good time to jump in with the homebrewed example problem. So now in this problem, oh, okay, cool. Well, here, let's now might be a good time to get at this anyway. So you'll notice that I didn't actually explicitly ask you to balance a chemical equation, but you're going to need to solve this problem. Okay. So let's take a look at this. So the first thing that we're going to need in this problem is a balanced chemical equation, and we're told that magnesium oxide which is made up of magnesium cations and oxide anions, right? So that's solid MgO totally. Parthana, thank you for being patient, and thank you for reminding me too. It's as you know, it's a long thread. So that's our reactant. Magnesium oxide decomposes into solid magnesium metal and oxygen gas. And the thing to remember about oxygen is that it's O2, right? So our balanced chemical equation, we need 2 oxygens on our reactant side, but multiplying MgO by 2 means we need 2 magnesiums on our product side. So this is our balanced chemical equation, all right? So we have, we're told that this reaction takes place at, 406 degrees Celsius in a 32.0 liter reaction vessel, and that we have 22.0 grams of magnesium oxide, and we're asked to find the pressure of O2. Right, so now that we've kind of condensed all the information of this problem down, we can get to work on solving. Okay. So we need to find the pressure of oxygen gas, all right? That means that we are going to be needing to use the ideal gas law, right? PV equals nRT. Now, we know our volume, right? It's right here. We know our temperature, it's right here. And we always know our value for R, right? R is the ideal gas constant. It's the same no matter what. If we want to find our pressure of O2 gas, that means we need to find our moles. And we're not given moles, but you'll notice we are given a mass of magnesium oxide. So we can do some stoichiometry to convert from 22 grams of magnesium oxide to moles of O2. First, we need the molecular weight of magnesium oxide to convert from grams to moles. Then we use the balanced chemical equation to convert from moles of magnesium oxide to moles of O2. All right. So oxygen, as we know, has an atomic mass of 16.00. Magnesium is 24. I want to say 24.13, but let's check our trusty periodic table. Oh, 24.31. Close but dyslexic. 24.31 plus 16.00 gives us a molecular mass of 40.31 grams of magnesium in 1 mole. And then our mole-to-mole ratio here is 2 moles of magnesium oxide react to make 1 mole of oxygen. All right, so grams of magnesium oxide cancels, moles of magnesium oxide cancels, and we're ready to crunch our numbers. 22.0 divided by 40.31 divided by 2. Wait, hang on. That's not right. 22.0 divided by 40.31 divided by 2. There we go. I think I accidentally hit multiply. This gives us let's see how many, 3 sig figs, 273 moles of O2. Now that we know how many moles of gas we have, we can use the ideal gas law to find our volume, right? So, our pressure. So if we want to solve for pressure, that means we need to divide both sides of this equation by our volume. So pressure is equal to moles of gas times the ideal gas constant times temperature over volume. So we have 0.273 moles times the ideal gas constant, 0.0821 liter atmospheres per mole Kelvin, times our temperature. Now, we got to be careful. We know our temperature is 406 degrees Celsius, but we have to convert to Kelvin first. Right, so this will be 679 Kelvin. That is what we're going to plug in. All over our volume, which was 32.0 liters. Now you'll notice our volume unit cancels. Moles cancel. And our temperature unit cancels because we converted to Kelvin. So we're just left with atmospheres, which is good because we're solving for pressure. So 0.273 times 0.0821 times 679 divided by 32.0. So the pressure for oxygen ends up being 0.4, let's see, how many sig figs? 3. 476 atmospheres. All right, now, I want to say something. If you got 0.951 if this happened to you, it probably means that you forgot to balance or to use the balanced equation. So, oh wait. So there was some discussion up in here. Oh, dude, Esther, you were totally right. You were totally right. You should give yourself a high five. Thanks. Yep, totally. Always go with your gut. Okay, there we go. So this was good. I'm really glad we got the opportunity to try it on our own, to watch it worked out, so that we could catch our mistakes. Totally. Okay, so go team. This was a great learning moment. Okay, so I heard that we have a trip scheduled to Osmolarity Land. Okay, awesome. Chapter 8, number 95. Let's take a look. All right. Indicate. This is an interesting problem. So indicate whether the osmotic pressure is greater, less than, or equal to the osmotic pressure, of what? Of 0.10, or no, just 0.1. 0.1 molar sodium chloride. Indicate whether the osmotic pressure of 0.1 molar sodium chloride is greater than, less than, or equal to the osmotic pressure of ... and then they give us solutions. So before we dive in, I want to say a quick thing, just so we can understand. Just to know off the bat, greater osmotic pressure is greater osmolarity. All right, so if they're like, oh, osmotic pressure, what do we do? Just know that greater osmotic pressure is the same thing as greater osmolarity. So they're just asking us to compare the osmolarity of 0.1 molar sodium chloride to the osmolarity of whatever comes next. And the thing is, for NaCl, right, this is 1 sodium cation plus 1 chloride anion. So our value for I here is 2. So the thing to remember is we have a 1.2 osmolar solution of NaCl. And this is what we're going to compare to everything that comes next. All right. So for part A, let's take a look. Part A, 495. Where did you go? Here you go. We want to compare it to 0.1 molar NaBr. And again here, sodium bromide breaks up into sodium plus bromide. So our value for I is 2. So part A we have 0.2 osmol, right, osmolarity. NaBr. So these two have equal osmotic pressure. They're the same. Let's do part B. Part B, let's see. Part B is a 0.050 molar of magnesium chloride. All right, so here we have 1 magnesium ion plus 2 chloride anions. So our value for I here is 3. That would give us an osmolarity of 0.15 osmol. And so here, the osmolarity, the osmotic pressure of our sodium chloride solution is greater than the osmotic pressure of our solution of magnesium chloride. Here we have part C. Here we're rolling with a 0.1 molar solution of magnesium chloride. Again, our I value is 3 here. So our osmolarity is 0.3. This solution would have a greater osmotic pressure because it has a greater osmolarity. A, B, C, and D. 0.1 molar of glucose. The thing about glucose is it is non-ionic, and so it doesn't break up in any particles. Its I is just equal 1. So the osmolarity here would be 0.1 osmol. So this would have a lower osmotic pressure than our solution of lower osmotic pressure than the solution of sodium chloride we're given. Totally. Okay, let's see. So that was 95, chapter 8. Prathana, let me take a look at those. Let's see, 101, 113. Okay. Okay, so here's what I'm gonna say. Excuse me. Ba-dum-ba-dum. Here's what I'm gonna say. Brianna, I will totally brew up another percent unit problem with density, and I'll write it on the board, do some of these, and then we'll circle back to it in a little bit. Then Carenza. Concentration problems. Give me 1 second here. Okay. Prathana, I see what you're referring to. Those are problems that involve concentration units, like Yeah, Brianna, exactly. Okay, let's see. So I'm gonna homebrew a concentration problem. Let's see. Yeah, that's what that means. What is the percent mass of a 50.0 milliliter solution with a density of 1.081 grams per mil oh sorry, I should say a solution of solution of sodium chloride with a density of 1.081 grams per milliliter and a molarity of 0.350 molar. Let me just make sure I gave you enough info. Yep, okay. There's a good homebrew problem right on the spot. Let's see, let's do number 113 and 117 from chapter 8. Alright, so consider two solutions, A and B, separated by a osmotic semi-permeable membrane that allows only water to pass through. Alright, so we've got semi-permeable membrane, we've got solution A and solution B. So the water is free to move backwards and forwards. Based on the following identities for solutions A and B, indicate whether the liquid level in compartment A with time will increase, decrease, or not change. All right. So here's the question. Oops. Does the water level of solution A increase, decrease, or remain the same. Now here's what that question is asking. All right, here's the question under the question, so to speak. It's asking you to compare, what you want to do is compare the osmotic pressure. Right? The osmolarities. All right, this is how you solve this problem. You compare the osmolarity of each solution if there's three scenarios. Osmolarity of A is equal to the osmolarity of B, then it's going to remain the same. The level in A will remain the same. If the osmolarity of A is less than the osmolarity of B, that means B has a greater osmotic pressure and A has a lower concentration, it's more dilute, so it will flow from A to B, water will flow from A to B, and so the water level for A will decrease. Finally, if the osmolarity of A is greater than the osmolarity of B, that means that B is more dilute, water will flow from B to A, and the water level on side A will increase. Okay, let's see. Lecture Wednesday. Yeah, totally. I will go grab that. Let me finish working this problem and then we'll bounce to that guy. Okay, so this is what we need to solve it. If the osmolarities are the same, no change. If the osmolarity of A is lower, its volume will decrease as the water flows towards the more concentrated side. If the osmolarity of A is more concentrated, it'll increase because water is flowing to the side of A. So let's take a look. So, solution A has a concentration of 1.0 molar sodium chloride, and solution B has a concentration of 2.0 molar sodium chloride. All right. The value for I for each of these is 2. So we have 2.0 osmolarity compared to 4.0 osmolarity. Here A has a lower osmotic pressure than B. That means water is going to flow towards B, and A will decrease. All right. And this is what you do for each one. You have to calculate the osmolarity for each, and then based on that original panel I wrote up, make the determination. Let's actually jump to. Wait, hang on. Let's jump to the problem that I did at the end of lecture, just because it might take a little time. I'm looking it up now. So at the end of lecture from July 8th, let's take a look. Well, let's see. My lecture on 7, 8. Oh, at the beginning of it. Okay, sorry, I was looking at the end of it. I'm like, I have an hard time seeing a problem. Let's see. Oh, wow, okay. Yeah, this looks like a pretty intense problem. Let's give this a whirl. So this is a lecture example 7, 8. At the start. All right, so we're told here that nitrogen trihydride gas. Here, I'm gonna put this over. All right, so let's see. So we have nitrogen trihydride gas decomposing into nitrogen gas and hydrogen gas at 212 degrees Celsius under 0.73 atmospheres in a 15.0 liter metal cylinder. So first we're asked to balance. So we have NH3 decomposing into N2 and H2. I'm going to just balance this really quick, mostly because time is short. And you can go back and review balancing chemical equations if you need to. But I'm guessing that's not the reason why this problem got requested. All right, so there's the part A, balanced chemical equation. We're told that this decomposition happens under 0.73 atmospheres of pressure in a 15-liter metal cylinder at 212 degrees Celsius. And we know that when we're doing gas stuff, we should immediately convert that to Kelvin. So that would add to 485 K. All right, okay, now part B, if all the nitrogen trihydride completely decomposes, what is the total pressure in the cylinder? What is the total pressure in the cylinder? So this is a great example of a Dalton's law of partial pressures problem. We're asked to find the total pressure, which is equal to the pressure of N2 plus the pressure of H2. All right. There's a couple different ways to solve this problem, but no matter how you solve it, you're going to need to use the ideal gas law, because the partial pressure of nitrogen times the volume, right? And here the volume is just going to be the same, because our volume is 15 liters for nitrogen and for hydrogen. They're in the same vessel. Is equal to the moles of nitrogen times R, and again, R is the same for nitrogen and hydrogen, times the temperature. And again, these two things happen in the same reaction vessel. The temperature is the same for both gases. So the pressure of hydrogen is equal to the volume of hydrogen times the, or pressure times the volume is equal to the moles of hydrogen times R times T. R is the same, temperature is the same. All right, so if we want to find pressure, we've got to divide by our volume. I'm sorry, both sides by our volume. So the pressure of N2 is equal to the moles of N2 times R times T over V, and the pressure of H2 is equal to moles of H2 RT over V. Now I'm going to do something that's a little, I don't know, it's like an algebraic massage. I'm going to move the N2, the moles, outside of a parentheses, and you'll see why in a minute. I'm going to do this for both expressions, for moles of N2 and moles of H2. All right, the reason why I'm going to do this is we now have an expression. The pressure of N2 is equal to this. We're going to substitute it in here. We also have an expression, the pressure of H2 is equal to this, and we are going to substitute it in here. All right? So, we need to go to a new slide. When we do that, we go from having an expression, total pressure is equal to the pressure of N2 plus the pressure of H2. We now get subbing in for the pressure of N2. There we go. So remember the pressure of N2 we had written in green there. It's equal to moles of N2 times RT over V plus subbing in for the pressure of H2. Pressure of H2 is equal to the moles of H2 times RT over V. All right, now you'll notice we have a common factor. So we can factor that out to get an expression for total pressure is now equal to RT over V, right? We factored that out, times the moles of N2 plus the moles of H2. And you'll notice that we have been given, we know R, we know temperature, we know volume. We just need to find the moles of N2 and the moles of H2, and then we're golden. All right, we're golden. Now, to do that, to find those moles, we're going to need to use our balanced chemical equation. Which I'm just going to rewrite right here. We need our balanced chemical equation, and to find our moles of NH3, and then use our balanced chemical equation to find that. So sorry, let me grab my okay, so we have pressure of ammonia. Yeah. Times volume equals moles of ammonia times RT. We want to know what our moles of ammonia are so we can find our moles of N2 and H2. So moles of ammonia is equal to the pressure of ammonia, which we were given, 0.73 atm, times the volume, 15.0 liters, over R, which is always 0.0821 liter atmospheres per mole Kelvin, and then our temperature was not given to us in degrees C. Oh, but we already converted that. So that's 485 Kelvin. All right. Now, temperature cancels temperature. Atmospheres cancels atmospheres. And liters cancel liters. So we can find our moles of NH3. We go 0.73 times 15.0 divided by 0.0821 divided by 485. So our moles of ammonia, keeping 2 sig figs, 0.2, oh, that's the sloppy 2. 0.27 moles of NH3. All right, we can use our balanced chemical equation to convert from moles of NH3 to moles of N2. And we can use our moles of ammonia to convert from moles of NH3 and our balanced chemical equation to moles of H2. For N2, 2 moles of ammonia produce 1 mole of N2. For hydrogen, 2 moles of ammonia produce 3 moles of N2. So 0.27 divided by 2 is 0.14 moles of nitrogen. 0.27 divided by 2 times 3 is 0.41 moles of H2. And now you'll notice we have everything we need to solve for our total pressure. All right, so hop into a new slide. Total pressure equals RT over V times moles of H2 plus moles of N2. We now have all these quantities. R is 0.0821 liter atmospheres over mole Kelvin times temperature, which is 485 K, over volume 15.0 liters times 0.14 moles plus 0.41 moles. Well, we got to do our addition first. So total pressure is equal to 0.821 liter atmospheres per mole Kelvin times 485 K over 15.0 liters. Equals 0.55 moles. Moles cancel moles. Liters cancel liters. Kelvin cancels Kelvin. And we have 0.0821 times 485 times 0.55 divided by 15 gives us a total pressure, total pressure of, let's see, 2 6 figures, 1.5 atmospheres. Alrighty. Yes, Brianna, we can totally go back over that concentration unit. Problem. Group 1A. To be totally honest, I'm trying to remember what's on there, but I don't remember specific groups, what made it onto the exam and what didn't with respect to the solubility rules. So anything in the solubility rules in the book, or anything that we covered in lecture or in the book for solubility rules are fair game. I think is all I can say at this point, because I don't remember the specifics. Let's see. There we go. Okay. Okay, so Brianna, this is the problem that I brewed up earlier. This will probably take us to the end of office hours. So let's go ahead and dive in. What is the percent mass of a 50 milliliter solution of sodium chloride with a density of 1.081 grams per milliliter and a molarity of 3.5 or 0.350? All right. So the first thing is we got to know what we're going after, right? We need to know the percent mass, which are going to be grams of solute over grams of solution times 100. All right, that is what we got to find. Now, you'll notice that our denominator, to get the mass of the solution, we can do that using the density of the solution and the volume. So these two together will give us the mass that go in our denominator. The trickier part is, how do you get at the grams? Well, we're given molarity, and we're given volume. Molarity and volume can get you to moles of solute, and to go from moles to grams, we can do that using the molecular weight. All right, so that's kind of the strategy that we're going to use to move from molarity and volume to moles, moles to grams. That'll be our numerator. And then we can use the density and the volume of the solution to get the mass that will go in our denominator. So that's our plan of attack. Jen, thank you for asking. His birthday was awesome. He ate cake and there were balloons, and his two best friends. So he's two, right? His two best friends are he's got a cousin who's 3, who's 1 year older, and then a cousin who's 1 year younger. And they're his two best buds. They're both girls, and he's a dude. But he loves playing with them so much. So they came over and we had a bunch of balloons, and it was just mayhem and toddlers and a good time all around. Thank you for asking. So first, let's find that mass of our that mass of our solution. So we have a volume of 50.0 milliliters of solution. We can multiply this by our density, right? 1.081 grams per milliliter. They are the three amigos. That is well said. Their names are two of the first non-immediate family names that he learned. They're pretty cute together. Okay, so, and I'm stoked that they're all close. My cousins all lived hours away when I was growing up, but they're all 30 minutes from each other, which is pretty awesome. So we have 54.1 grams of solution. That's going to be our denominator. Now for our numerator, we have a molarity of 0.350 moles of sodium chloride over liters, and to cancel our denominator, we need to multiply by our volume, but we have to convert our 50 milliliters to liters first. So volume, liters cancel liters. Now we're left with moles. Second, we got to convert from moles of sodium chloride to grams. Sodium has an atomic mass of 22.99. Chlorine is 35.45. So let's go ahead and add these two together. 22.99 plus 35.45 is 58.44 grams per mole. Now moles of sodium chloride cancel, and we have 0.35 times 0.0500 times 58.44 gives us a mass, a mass. That's exactly what it is. Rounded to 3 sig figs of 1.02 grams of sodium chloride. All right. Now, with that in hand, we can calculate our mass percent, because we take our grams of solute, 1.02 grams, divided by our mass of solution, 54.1 grams, times 100. 1.02 divided by 54.1 times 100. Let's see, rounded to 3 sig figs gives us 1.89% mass to mass. And that is our final answer. Let's see. Number 65, chapter 8. Let's see, I think we do have enough time for one more dude. Let's see, 65, chapter 8. Let's take a look. All right, what is the, so here. Number 65. What is the molarity of a solution prepared by diluting? Okay, so we have 25.0 mils of 0.220 molar sodium chloride. And then diluted to each of the final volumes. Brianna, you are welcome. And the thing is, so, for example, in part A, they tell us to dilute it to 30.0 milliliters. Well, this is a dilution problem, right? M1 V1 equals M2 V2. And this is a dilution problem where they're asking us to find the final molarity each time, because they're giving us, they've given us M1 here, they've given us V1 here, and V2 is given in part A, so they want us to find M2 every time. So if we divided if we divide both sides here by V2, we get M2 is equal to M1 times V1 over V2. And now we just plug in our values. M1 is 0.220 molar. V1 is 25.0 mils. And V2 is 30.0 milliliters. Milliliters cancel. And let's see, crunching our numbers. 0.220 times 25.0 divided by 30.0 would give us our final volume, our final molarity, rounded to 3 sig figs of 0.183 molar. So, chapter 8, number 65, is just a dilution problem. I guess what I would say is alrighty, that brings our office hours to a close. I know that the exam, the third exam, is going to be a challenge, but I also know from hanging with all of you both Tuesday and today that you all are up to the challenge. So I wish you the best of luck. May the force be with you. And we will be back at it for our final week, starting on Monday. Later, dudes.